Welcome everyone. Thanks for being here to the next session at CHEC World 2023. Good to have you here. Today I will take you on a journey towards the use of sensors in mold to characterize the material and artificial intelligence to make use of sensor data and to transform the information into information you need to control the process into quality criteria of the material. My name is CHALOUPKA. I'm Managing Director of NETZSCH Process Intelligence, and I'm here to present you our product, sensXPERT Digital Mold, that brings you a step further into digitalization and make use of sensor data in composite manufacturing. Who we are. Most of you may know NETZSCH from laboratory equipment, so material characterization in the lab. I'm on my way now since more than 10 years on paving the way and bridging the gap in between material data created in the lab in a safe and secured environment and bring it into the manufacturing environment to really make use of that and to get rid of the deviations we have in between laboratory and the real process environment. What is sensXPERT about? sensXPERT is a solution that uses sensors installed in the mold. We offer sensors with a dielectric measurement principle characterizing the material in the mold. So we see the flow behavior, we see curing, crystallization, and we transform the information into degree of cure, degree of crystallization, and glass transition temperature to have quality indicators for the process to be stopped. These sensors communicate with an edge device. Even there, throughout the last years, we've seen digitalization is not an easy topic. We have so many different solutions in the shop floor, whether it is automation in automotive industry, aviation, machining, electronics. There are so many different solutions. Each machine manufacturer has somehow its own solution. And we have seen to pave the way to make use of characterization data based on sensors, we need to create an own edge device that is connected to the sensors, even to third-party supplier sensors like pressure or temperature, and is communicating with the machine to exchange machine parameters and material data back and forth. So what we do in principle is we combine three data sources on this edge device. We combine the real-time sensor data that are created during the process. We combine material science, so reaction kinetics of the materials that are getting characterized and are used for production, and machine parameters. And all the three data sources we combine in machine learning models on this edge device. So in real time, the edge device uses all the data information and transforms it into quality criteria of the material, so degree of cure or glass transition, for example. From here, we have the possibility to see how the material behaves, even if the material has aged or is affected by environmental changes. And we send the data into the sensXPERT cloud. The cloud environment is the central interface for our customers with the process, with the information that are generated during the manufacturing. And in addition, besides the visualization of all the data, we have AI also implemented in here because, as you can imagine, from the beginning on, we cannot know every failure mode that can occur during production. But as soon as new data occurs and shows up with new information, and we get the feedback from the customer if it's an okay or a not okay part, we can train the model based on that. And we use deep learning algorithms in the cloud environment to retrain the models that are later used on the edge device in the shop floor again. While doing so, this package is a solution bringing you a device and the software environment to take care about your process, to get a deeper insight, to gain transparency, and to transfer quality control currently done as a post-process QA into the process. So our target is to give you the possibility to see how the material behaves in the process and to give the information to the machine to adapt the process parameters if we see deviations in there. How is it working? As already mentioned, we combine sensor information together with material science, so reaction kinetics that has been generated in the lab environment. While doing so, we can have a simulation environment that gives us the possibility, once we monitor the first in-process data on the customer side, to simulate how the material behaves under different circumstances, so in the easiest way, under different temperatures. And if you think about today's material data sheets, then you can sometimes find a suggested temperature profile that should be used to produce parts with it. But the reality shows that you usually don't use the cycles that are in there. You play around, you try to find the right cycle for your design of the component. And then you need to find the best cycle in terms of cycle time, shortening the cycle times. But on the same side, you have to care about the safety. And this is what we have combined and how the machine learning model acts in real time to be able to adapt the process parameters. And what you can see here is how the machine learning models act in real time. So what you can see here is an example from the aviation industry where you can see the ground truth, so the real material behavior, and you can see another curve that is shifting a little bit. This is what the machine learning models is calculating and predicting in real time. And even there, what you can see here, roughly around 90 minutes, we are already in charge with the information we have collected until then to predict the next 80 minutes. How will the material behave based on what we've seen from the material in the first 90 minutes? And with the cloud environment, you are the one who has the full control over the entire manufacturing data, even historic data. And you have the possibility to give us the feedback if a data set is connected to a good or a bad part. If we tell you, hey, there is a data set where we don't know if it's a failure mode or not. So the model has to retrain itself step by step, and we have to involve you as a customer to give us the feedback if we see something strange in the signals, to be able to identify what it is and to tell you in the future based on what we've learned if it's an okay part or a not okay part. And based on that, we have started with the target to reduce cycle times and to avoid scrap. But there's much more. We've seen with customers from aviation and automotive that there is a bigger target behind. So the numbers that are generated while reducing the cycle time and cutting down scrap is that we reduce the amount of energy that needs to be used to produce one single okay part at the end. And even there, we perform the quality control in real time in the mold, so you don't have to wait until your QA lab says this batch of material is okay and can be sent out to the customer. Two use cases. I want to show you that you get a feeling of what the system can do. And I will also show you the return of investment calculator. What does it mean for two different industries? Here we have a composite material, an epoxy molding compound with a lot of fillers with a target to have a high electrical insulation for the automotive industry, so electronics encapsulation. And the second use case will be about aviation, where you see when we talk about the use of sensors and AI in the composite industry, we have a broad breadth of technologies we can use, whether we talk about transfer molding, injection molding, resin transfer, high compression molding, vacuum infusion, autoclave curing. So where to use the technology doesn't matter. But the benefit for the different industries is a little bit different. So we are talking about high performance parts, where we talk about high mass production, or where we talk about low volume, but very cost extensive components. So one use case from a tier one in the automotive industry located in Germany is electronics encapsulation for a new generation of e-motors. So there's also a German OEM behind. And where we've started here is we have seen the material supplier says that the shape of the material will be stable once we reach a degree of cure of 70%. In reality, our customer uses more than 90% degree of cure just to make sure that we don't have a warpage problem or something else at the end. So you can imagine if we stop at 70%, we demold, the part is assembled to the car, and then it's heated up again, that we can have a warpage problem and we will damage the electronics. So what we've done here is, we have done, after creating the machine learning models and convincing the customer that we can reduce the cycle times, we have done a serious manufacturing simulation. What you see here are real parts, 150 parts in a serious manufacturing simulation, where we have had a look to the real material behavior, so the scattering of the dependency between curing time and degree of cure, and the curve you would get from reality if you characterize the material in the lab and you want to rely on what you've characterized there. So you can see we have a scattering around the reality. In principle, there is a trend between cure time and degree of cure, but in reality, and here we have really fixed the parameters, and we have used one batch of material with this customer together. And this is what you get out of that. And this is how we can use sensor information and AI to adapt the cycle to how the material behaves, and not to fix the cycle time and the process parameters to an unflexible system. So what you see here is that we have shown together with this customer that saving 20% of cycle time is the reality, just while having the chance to look into the process and to adapt the cycle time. That means we have parts here where we can reduce the cycle time by 20%. We also have parts in here based on the scattering where we just have the potential of reducing the cycle time by 10%. But that makes it much more important to have a dynamic process control based on the material behavior. And this brings us then forward on the way to have a more sustainable production and to make use of the data that are already available. So also here, the model is used to not just calculate degree of cure and glass transition temperature in real time, but also to predict it quite early in the process, to know already what kind of material do we have in front of us. Do we have a batch-to-batch deviation? Do we have an aging in the material? So this is how we use the data to transfer manufacturing processes for the future. And when we look to the return of investment for this customer here, we are talking about a high volume manufacturing, so more than 4 million parts every year. And we can see, while using our technology, in the same time, our customer can produce, so over 1 year, more than 200,000 more OK parts in the same time frame. And transferring that to the order of this German OEM that is behind this case, we have seen that the serious manufacturing calculated for 3 years on 4 machines can be reduced down to 4 machines and 2.75 years of manufacturing time. So a quarter of a year can be used to set up a new process, to use the existing resources for new processes, scaling up the manufacturing potential, while ensuring that the quality of the parts is constant and on the same level. Now, the second use case, the aviation industry. Here we talk about totally different amount of parts and a totally different cycle time. But also here, when we look at aviation structures, where we definitely have a target degree of cure of more than 90% and a cycle time of 400 minutes in this case, we have seen, even if in a cascaded process, that we see deviations in the first process step, and based on these deviations, we can look into the future. How will the material behave in the next process step? And what we see here is the manufacturing protocol of this case works well at the end customer, but the money that is laying on the street is huge. And here we are talking about 25% of cycle time reduction, just while having the chance to look into the material behavior during manufacturing and to transform the information into degree of cure and glass transition temperature. So even there, the AI capability, and here we are talking about a long time. We can not just adapt the process in real time, we can even send a signal to the logistics to change the entire process route of these parts, so to increase the throughput. And if you remember on the time before COVID, the order books of Boeing and Airbus, they were overfull, and they didn't know how to manufacture all these planes. And now we are coming back to more or less the same level like before COVID. So we have to do a lot in every industry to act more sustainable and to reduce cycle times, costs, and energy consumption during the production of every single part. If you look at the numbers, totally different. Here we are talking about many million euros that are laying on the street in this industry while manufacturing composite structures. And this is huge. And if we transform these 25% into more planes, then we can calculate that we can manufacture, at the end, 25% more planes. This is just one step and one very important brick on the way to transform the manufacturing with digitalization, and here in this case, make use of sensor data and AI to digitalize manufacturing, to gain transparency, and to go or to pave the way to a more sustainable production. So thank you so much for being here. I wish you a nice third day and end of the second day. And if you're interested in the technology to hear more about and to get to know or dive more deep into the detail, what we are doing, how we are doing that, please visit us here in Hall 6 at the booth R32. And now I'm open for questions. We have still a little bit of time. Do we have questions? Over there.
Hello. Is there a lifespan limit to these sensors embedded in an autoclave tool or something like that?
Exactly. Can you repeat the first part of the question, please?
Do these sensors that are embedded in an autoclave tool or other, do they, after subjection to heat so many times, do they have a limit and need to be replaced? And does that affect the business case very much?
I cannot give you an exact number because it's always depending on the use case, but the sensors have been designed on requirements of the automotive industry to withstand at least 15,000 cycles. But as you've seen here, we have a use case in the electronics industry, and there we have had the sensors now for 2 sensors, more than 1.2 million parts having been manufactured with the same sensors, and we don't see that the sensors got damaged or something else. So the sensors just consist of stainless steel and a small ring of ceramics. So. Some other questions? Over there?
Hello, I'm Marie-Laure Chensek from Dassault Systèmes. So this is really a beautiful offer. My question is about the data set for building the models. Obviously, you will need to have enough data to have accurate models, so it will demand some time, because I imagine none of our clients have already ready the data sets to build those models. So can you say more on the timeline of a full project, I would say, to be able to have accurate models?
Yes, for sure. Very good question. So you're totally right. If you think about AI and data science today, we already think about big data that are used to train the models. While combining material science from the lab and the real-time data from the sensors, we have paved the way to build a simulation environment that gives us the possibility, once we have the first reproducible data on the customer side, and this can be already on the first day, to combine this with the pre-analyzed material data from the lab from material science, so with reaction kinetics. And this brings us into the position to generate 100,000 of data sets with temperature deviations or humidity deviations based on material science already there from the lab in the materials database we have, and the real-time sensor data. So from here we start to train the models. So in the best case, we install the package on one day. We manufacture 10, 20, 50 parts the first day. The data are reproducible. Then we start to train the model based on additional simulated data. So overnight, then we simulate the data, we train the model, and the next day we can work with the machine learning model on the customer side. But what I mentioned before, we don't know every failure mode from the beginning on. So here, we also need to involve the customer that once we identify a data set that is not known so far, to send the information to the customer and request feedback to label the data as an okay or not okay part in the best way with additional information about if the part is not okay, what is the failure, that we in the future can identify that. Because this information is then used in the cloud environment with the deep learning algorithms to retrain the model, to send it down to the edge device, to the shop floor, and then the next time this specific data set occurs, we know what's the state of material and what to do. We have 3 more minutes. Additional questions? Doesn't look like. Then I would say thank you very much for being here. If you're more interested in the technology, please visit us in this hall 6R32. And thanks for being here. Enjoy the rest of the JEC World 2023. Thank you.